Le Chatelier's principle is the next concept that we're going to cover. And this is an interesting concept because so far what we've been talking about is we've been talking about equilibrium reactions and what is required to achieve equilibrium. And now with this concept, what we're going to be doing is we're going to be talking about ways that we can disrupt that equilibrium. So a reaction that wasn't at equilibrium that then became or achieved equilibrium. Now these reactions that are in a state of equilibrium, we're going to look at what can we do to disrupt those. And when those are disrupted, what effect is that going to have on that reaction? How is it going to behave? And what can we predict is going to happen to the reactants and the products based on these disruptions that we're going to place on these equilibriums. So you take a look at the board here, you can see that there's three methods that we can use to disrupt an equilibrium. And these are what we refer to as just stresses on the equilibrium. And so we've got concentration changes. If we change the concentration of either the reactants or the products of a reaction that is at equilibrium, then there's going to be a disruption to that equilibrium. It's not going to be an equilibrium anymore. And what is that reaction going to do to get back to that state of equilibrium? We can also change the pressure and we can also change the temperature. And these are the three stresses that you can place. So the analogy that I like to use to describe this and how this is analogous to maybe a real life situation is if you take a hair elastic, for example. If you think about a hair elastic, has a particular shape. And if you squish that hair elastic up into your hands, you're disrupting the shape of that hair elastic. Now, if you release your hands, though, that hair elastic is going to bounce back to its original state of sort of this oval-y looking shape that they normally have. Similarly, if you take a hair elastic and you stretch it and you make it larger, as soon as you relieve the stress on that hair elastic, in other words, you let go, that hair elastic is going to go back again to its original state, the state that it wants to be in, where it's the most happy. And equilibrium reactions are no different. Equilibrium reactions want to be in equilibrium. And whenever they're taken out of equilibrium, their shift that you're going to see in those reactions is going to be so that that reaction can get back to equilibrium. And so we'll look at each one of these stresses, how each stress affects the equilibrium, which way the reaction will shift, and give you some information so that you can make those same predictions for this concept. So we'll be right back with our first one, concentration changes. Okay, so here's the first kind of stress that we can place on an equilibrium, and it's a change in concentration. Now, I'm going to try and use colors here to kind of help dictate to you what is the stress, and you're going to see lots of arrows here on the board. This is just showing how things are either going up in concentration or down in concentration, and which way the reaction is shifting. Now, by a reaction shift, what I mean is that, for example, if this reaction is going to shift towards the products, all that means is that this forward reaction arrow is going to like run in hyperdrive. It's going to run a lot faster than the reverse reaction would. And so number one thing you need to know is anytime we stress an equilibrium with one of these three methods, the equilibrium reaction is now no longer at equilibrium. And that's why it shifts either the forward reaction or the reverse reaction into sort of like a hyperdrive mode, and that's so that that reaction can quickly get back into equilibrium as fast as it possibly can. So in scenario one here, this red arrow, usually the stresses I like to denote with like a little squiggly arrow. I've drawn it here in red as well, just for extra emphasis on the fact that this is the stress that we're placing on the equilibrium. We've got the Haber process here, which is just the formation of ammonia, and you can see that this is an exothermic reaction producing 91.8 kilojoules of energy for every 2 moles of ammonia that's produced. So what happens to this equilibrium reaction if we take out of the container that reaction is occurring in, take out the ammonia, or if we take out at least some of the ammonia? If we change the concentration by removing some of the ammonia out of the bin, then we have disrupted this equilibrium, and we're going to see a shift. Now, this reaction is going to want to shift in a way so that it can relieve the stress that was placed on it. So if there's an external force or stress that's placed on here where ammonia is being removed, this chemical reaction wants to replace the ammonia that was removed. So you have to ask yourself which reaction, either the forward or the reverse, is going to make more ammonia. And what you would simply determine from that is you would say, okay, well, if I want to make more ammonia, that means I need to use up reactants. So that means that I need to run the forward reaction into sort of this hyperdrive mode where it's going to make a lot more ammonia than it is going to be turned back into the reactants. And so this reaction shifts towards the products, that's what we say, and that is therefore going to make some ammonia to replace the ammonia that was taken out by us. Now you'll notice that I don't draw the arrow quite as large as the stress that was placed here. Typically the reaction doesn't produce or replace all of the ammonia before it achieves equilibrium, but there's an inherent effect on all the other things in this reaction as well, because this reaction is shifting towards the forward reaction, towards the products. And that means that if I'm going to be making some ammonia, I'm also going to be making some more heat. And so the temperature of this reaction is going to go up a little bit. And also, in response to that stress relief that's happening, obviously in order to make some ammonia, these reactants have to be used up in order to do that process. And so using that method of what is the reaction going to do to relieve the stress that's placed on the system, you can then predict what's going to happen to everything else in the reaction as well. So let's try another example. So let's say that we take out, here in scenario 2, the stress is we take out some hydrogen. So this is a reactant that we're removing. So what this reaction wants to do is it wants to relieve the stress that was placed on it. So if we've taken out hydrogen, this reaction is going to want to make more hydrogen, which means for this reaction, it's going to shift towards the reactants. It's going to run the reverse reaction a lot faster than the forward reaction. And so when that happens, now we can say, okay, the arrow's pointing this way, which means this is technically going to be the reactant side, and this is technically going to be the product side. And so these guys, concentration will increase, and these concentrations, or temperatures, if we're talking about heat, will decrease. And so you can again see how we can predict that. If you take a look at scenario number 3, again, same thing. This is the stress that's being placed on the system. We are adding some nitrogen to the system. So what is the reaction going to want to do? Well, it's going to want to relieve the stress that was placed on it. So if we add more concentration, then the reaction is going to want to take it away or use it up. And so how is this reaction going to shift in order to use up some N2? Well, it's going to shift towards the products. It's going to want to make some more products using up some of this. And so this concentration is then going to go down a little bit, and then inherently all of these other things are going to be affected as well. This concentration will go down, and this concentration will go up, and the heat of the reaction will also increase. So there's a couple of examples there for you to kind of process and look at how you can predict what a reaction is going to do, which way it's going to shift to relieve the stress that's being placed on it in terms of concentration changes. Next up is pressure changes, so I'll be right back. Okay, so pressure changes. I've got a couple scenarios here that I want to run through with you guys. First of all, what you need to understand is how the reaction is going to react or shift in response to this stress. So there's 2 stresses with pressure changes that we can apply to an equilibrium. Either you're going to increase the pressure or you're going to decrease the pressure. And the way that the reaction will shift depends on how many moles of gas are on either side of the equation. So as you can see, for an increase in pressure for a reaction that's at equilibrium, the reaction will shift to the side that has less moles of gas. And so if we were to do this scenario right here where we have an increase in pressure, what you always want to do is when you're determining which way what's all going to be affected in the equilibrium reaction, the first thing that you have to identify is which way will the reaction shift to relieve that stress. So an increase in pressure tells us that it's going to shift to the side with less moles of gas. Now you can see that all of these substances here are gases, so I have to take into account all of that. This side of the reaction has a total of 2 moles of gas. This side of the reaction has a total of 4 moles of gas, 3 hydrogen and 1 nitrogen. And so the side that has less moles of gas is the product side. And this is something you just have to memorize and know that when an increase in pressure happens, it's going to shift to the side with less moles of gas. And so this reaction is going to shift to the side with less moles of gas, the product side. And so if this reaction is running mostly in the forward direction, now I can determine what's going to happen to all of these other things. This is making these be used up, because those are technically the reactants, and these would be the products, so they would increase in amounts as well. For a decrease in pressure, you can imagine the opposite is true. So if I decrease the pressure of a reaction that's at equilibrium, it's going to shift to the side with more moles of gas. And so here's scenario number 2, a decrease in pressure. Obviously this side has more moles of gas, it's got 4 moles. And so this is going to shift or run in the reverse direction a lot more than it would in the forward. And so then these concentrations would then be changed to an increased value, and these ones would go down. And the thing about pressure is, why does it do this? You just have to think about a container. If you're increasing the pressure, what you're doing is you are making less space for the moles of gas to exist. So if you increase the pressure here, really what you're doing is you're making a container a lot smaller. And if the container is a lot smaller, then there's less space for the gases to exist. And so to relieve that stress, it's going to shift to the side that has less moles of gas, because if there's less moles of gas in the container, then it's going to help with the pressure change that equilibrium reaction is experiencing. Likewise, if you decrease the pressure of a reaction, essentially what you're doing is you're making the container larger. And so if you make the container larger, now it has more space for those gas molecules to be in. And again, when a reaction's at equilibrium, it's happy, and when it's disrupted, whether it's an increase or a decrease in pressure, it's still a disruption. And so it wants to do whatever it can to relieve the stress that's placed on it. So if the stress is you're decreasing the pressure, it wants to ramp the pressure back up a little bit by shifting to the side that has more moles of gas. And so that's it for pressure changes. Last up is temperature changes, so be right back. Okay, so temperature changes is the last type of stress that we can place on an equilibrium system. And we'll just take a look at these 2 quick scenarios, and then we'll jump into a quick little summary. Essentially, temperature can either be increased or decreased, just like pressure. Okay, so there's really only 2 scenarios that you can really look at. And because we've done the heat unit already, you know that energy terms go into the reaction like this. So if it's an exothermic reaction, then you're going to see an energy term over here. Some reactions are endothermic, you're going to see an energy term over here. Wherever the energy term is, that's the stress that is going to be placed if it's a temperature change. So here you can see that this is an exothermic reaction, and if I increase the temperature that this reaction is operating at, that's the stress that's being placed. And this reaction is going to want to shift to the side of the reaction that's going to relieve that stress. So if I make the temperature go up, the reaction is going to want to make the temperature go back down. And so in order to make it go back down, which arrow is going to run faster, forward or reverse? The answer is, for this one, the reverse reaction is going to run a lot faster. And that is because it wants to use up the heat that was just put in. And the only way to use up the heat is to make the reaction run like this. So these will all go down, and then inherently all these other things will be affected like that. If you look at scenario number 2, where instead we're not increasing the temperature but decreasing the temperature, then obviously you would see that the reaction would shift towards the product side to relieve the stress. In other words, it wants to make more heat because heat was taken out. And so then a forward reaction, you're going to see these arrows go up and these arrows go down. These arrows go down, again, just to recap, because in order for these things on the product side to be made, I have to use up both of these substances here to make that happen. And that's temperature changes. So I'll be right back with a quick little summary and a couple more pieces of information for you, and then we'll be done this concept. Okay, so a quick little recap on Le Chatelier's principle and a couple final little concepts that you need to know. First of all, here are the 3 stresses that we reviewed. These are the ways that you can disrupt an equilibrium, take it out of being in equilibrium, and then we learned some principles to be able to show how the reaction is going to behave so that the reaction can relieve the stress that was placed on it and how that affects everything else in the reaction. So we've got concentration changes, pressure changes, and temperature changes. Now, one thing that you need to know about these stresses is that whenever we make concentration changes or pressure changes to an equilibrium and disrupt the equilibrium, that equilibrium reaction will undergo a shift so that equilibrium can be achieved again. And when equilibrium is achieved again, you'll notice that the Kc value will always be unchanged anytime we make one of these 2 changes. However, if we put a temperature stress on an equilibrium, then the Kc value does change. Now, there's a whole bunch of complicated math that is totally unrequired for this course. So what I need you to do is I need you to just take my word for it and just trust me that these changes and no changes in terms of concentration and pressure are true. So this is something you just memorize. Don't worry about the math behind it. Just know that for these 2, Kc is unchanged, and for temperature changes, Kc does change. This was the reaction that we used for all of our examples for this. And what I wanted to point out was for pressure changes, you'll notice this one was really easy to determine that which way it was going to shift, because this side had less moles of gas than this side did. But sometimes you're going to come across a reaction, hypothetically, for example, this generic one, where you've got the same number of moles of gas on the reactant side compared to the product side. And if that's the case, then these pressure changes, it will, the reaction, you're not going to see any shift for this. It's not going to shift to one side or the other to relieve the stress, because no matter which side it shifts to, it's going to be in the same state that it currently is in. So it just kind of deals with the situation. There's no shift that you observe whenever you have the same number of moles of gas on the reactant side to the product side in a situation where there's a pressure change. And the last thing that I wanted to point out was sometimes you're asked questions about catalysts and how does this affect equilibriums. And what essentially a catalyst does, if you remember from Science 9 and maybe a little bit of Science 10 and Chem 20, is that catalysts speed up the reaction. So for equilibrium reactions, because we kind of have 2 reactions simultaneously occurring in the container, if you add a catalyst, it's going to speed up both of those reactions, the forward and the reverse reaction, at the same rate. And so essentially you would have, if you were to add a catalyst, just larger arrows like that depicting that both reactions are running faster. But whether I'm changing products or reactants into products and products into reactants at a slow rate or at a fast rate like this, if the rates are equal, then it's at equilibrium. So adding a catalyst to an equilibrium reaction yields no change. You don't see any shift in the reaction, and in fact, you wouldn't even be able to observe any changes, simply because the net result is the same amount of products turning into reactants and vice versa. And so you just don't see any change. And that's all you guys need to know about Le Chatelier's principle.